This is the final episode in the series, and we'll cover proof by contradiction. I like this definition of the proof by contradiction because often students struggle to understand what to negate for the first step of the proof. But this makes it quite clear that we need to look for the statement, and the first step is to assume the opposite. The second part of the process is then to form a string of logical statements that eventually reach a contradiction. This part does not necessarily have a general approach, so we'll look through some examples in order to try and spot some similarities that you should look out for. For this first question, can you spot what the statement is that we need to negate? Here we have a very common structure in mathematics of if and then. In cases such as this, it is the statement after then that we need to negate, so we start by assuming the opposite, that n is odd when n squared is even. Now is the second part of the proof, the logical statements. We saw with the direct proofs that if a number is odd, then it can be expressed in the form 2k plus 1, where k is an integer. The next logical step would be to assess n squared, which we can see is of the form 2 times an integer plus 1. This leads us to our contradiction, as n squared is even. It is only n being even that we negated. We will see that many of the logical progressions of statements will look at expressing odd numbers in the form 2k plus 1, and even numbers in the form 2k. So always have this in your mind when looking at proofs involving even and odd numbers. Again, pause the video to think about what the negation of the statement would be. This is another if-then structure, so we can assume the opposite of m squared minus 4n minus 7 does not equal to 0. This is to assume that this expression does equal to 0. The only logical thing we can do now is to rearrange, and we can try to think about odd numbers and even numbers, as m squared can be expressed as an even number 4n plus an odd number 7. So therefore m squared must be odd. To be a bit more precise, I can factorise out 2 and show that it is 2 times a number plus 1. If m squared is odd, then m must also be odd, as only an odd number multiplied by an odd number will give an odd number. Therefore, we can express m as 2k plus 1, where k is an integer. I can now substitute this in, expand, and simplify. I can simplify this further by dividing both sides by 2. Now if we analyse both sides, we have our contradiction. The left-hand side is clearly an even number, as it is 2 times some integer. The right-hand side is an odd number, as it can be expressed as 2 times a number plus 1. This is our contradiction. We always need to have a statement explaining at the end exactly what our contradiction is. Again, even numbers and odd numbers are playing a big part in the logical steps, and something common we can see in this part of the proof. The next example uses a different wording for the statement. Pause the video and think about what the negation of this statement would be. As a hint, you could try and change this into an if-then statement. If you were to change it into an if-then statement, then it would be if p is prime, then 2p plus 1 is not a square. So our assumption would be that there is a prime p that exists such that 2p plus 1 is a square. We can therefore say that 2p plus 1 is equal to a squared for some integer a. What conclusion can you now draw from this statement? As a squared is 2 times an integer plus 1, we can say that a squared is odd, and therefore a is odd. So now we can write a as 2k plus 1 for some integer k. We can now substitute in, again, expand, and simplify. There are now two ways to analyse p. Firstly, we can now see that p is an even number, and hence must be 2. However, this is a contradiction, as 2 times 2 plus 1 is not a square number. Another way of analysing p is by factorising the left-hand side and forming our contradiction in this way, as p is prime, but clearly has at least 3 factors of 2, k, and k plus 1. Even if k were to equal 1, then it would still have 2 factors of 2 and 4. Again, we can see the importance of thinking about number properties, such as whether a number is odd, even, or a prime number. The final example is a famous case, and I want to go through this proof so you can see how these number properties do continue to be of use when tackling proof by contradiction questions. Again, pause the video to think about what the negation of this statement would be. Every time we want to negate something, there must only be 2 options. It either is something or it is not. There can't be a third option. In this case, a number is either irrational or rational. Therefore, our starting assumption is that root 2 is rational. This means it can be written as a over b, where a and b are co-prime integers. Being co-prime means the only common factor they have is 1, so this must be root 2 in its most simplified form. A rational number must have a simplified form of one integer over another. Furthermore, clearly a and b are not equal, as this would mean the fraction would be equal to 1. What logical step can you think of next? How can you manipulate this statement? Well, we can square both sides and then manipulate to see that a squared must be an even number, and therefore a must be even, so it can be written as 2k, where k is an integer. We can now substitute this and then simplify. We can now see that b squared is even, and therefore b must be even. This is a contradiction though, as both a and b being even would mean they share a common factor of 2, which means they are not co-prime, or it could mean that the fraction could be simplified further, but that is a contradiction to our assumption. Proof by contradiction does not have the same kind of generalized structure that induction had when it came to the proof part. But we can see some general things to think about when analysing your statements and trying to progress from one statement to the next. Think about whether a number has any factors, or whether it is an odd number or even number, and can be expressed as 2k plus 1 or 2k respectively.